could you put solar panels on the back of a phone and just have a solar powered phone? That's the question that we're going to calculate. We're going to estimate. This is not a phone because my phone's recording this video. This is an old iPod, but you get the idea. Okay. So, and this is a solar panel. Not a really great one, but you get the idea. Okay, so let's start with some estimates and some real data, and then we can calculate this. Okay, so the first thing is, how big is this phone? I just measured my actual phone, and I got 7 centimeters by 14 centimeters. That's how big it was. I also looked up the power, the energy in the battery, and this is not the energy, but it was close, so I just rounded up. So the battery was listed at around 2,000 milliamp hours. Okay, so we're gonna have to find the energy from that at 5 volts. That's important. Okay, that's the way they like to write batteries, milliamp hours, which means it would run this could run 2,000 milliamps for an hour at 5 volts. Okay. The other important thing is the solar intensity of light at the surface of the Earth. It's around 1,000 watts per square meter. And then we need one other thing, and I guessed at this, but I think it's an okay value. The efficiency E of a solar panel is around 25%. I'm going to go with that. Okay. So the first thing is, how much energy is in that battery? Let's do that. So this says, I know that power is the change in energy over the change in time. So the energy is going to be power times time. So let's say I have a time of 1 hour. 1 hour, can you see this down here? Yeah. 1 hour is 3,600 seconds. And I'm doing that because I like to get things in units of joules. And a joule per second is a watt. So the other thing is the power for this. If it's 2 amps, 2,000 milliamps is 2 amps. At 5 volts, I know the power is 2 amps at 5 volts. So that's going to be 10 watts. That would be true if it ran for an hour, because we're talking about the energy. Okay. So now I can take the power times the time, and I get the energy. So the change in energy for that battery in the phone is going to be the power of 10 watts, which is a joule per second, times 3,600 seconds. And I get 3.6 times 10 to the 4th joules. Right? Because 10 times 3,600 is 36,000, or 3.6 times 10 to the 4th. So that's the energy in the battery. So suppose I need that much energy, or let's just say I want to recharge my phone by putting it in the sun. Okay, and how long would it take? Well, now we need to look at the power, the solar power, P solar. Okay, that's going to be equal to the intensity of light times the area of the phone. And that's wrong, but let's just say it right now. So how big is my phone? Well, the area is going to be equal to 0.07 meters by 0.14 meters. Now be careful. I know that you would make this mistake, because I've already seen a bunch of students make this mistake. Not just this year, not just last year, but all the time. Okay? And that's the mistake of saying, oh, 7 times 14, I get the answer in square centimeters, divide by 100, and I get square meters. No. Okay? A square, oh, here it is. Okay, this is a box. Let's see, where's my volume? Okay, there's a centimeter. So it's that a little box like that is a square centimeter. A square meter is 1 meter by 1 meter. So like that. Okay, so it's not 100 of those. Not 100 square centimeters in a square meter. It's way bigger than that. The best thing to do is to convert to meters and then square it. Okay. So if I do this, I get an area of, I already did this in my calculator, 9.8 times 10 to the negative 3 square meters. Okay, So I have the area, I have the intensity. Now I actually also have to multiply by the efficiency, because all that light hitting the solar panel is not going to go into electricity. Okay, only 25% of it is. And it's even worse than that, because actually I need to take into account the flux. So if I have my phone at an angle and the sunlight's coming straight down, then I need this angle theta, and I should multiply by cosine theta. Now, so what angle should I use? I mean, you're going to carry the phone around. Sometimes theta is going to be 0, sometimes it's going to be 90. So let's just go in the middle. Let's go with 45. Okay, so I'm going to use an angle of 45 degrees. So now I get the power from the sun is going to be equal to 1,000 watts per square meter times the area of 9.8 times 10 to the negative 3 meters squared. And you notice the meters cancel, times 0.25 for the efficiency, times cosine of 45. And if you do that, I get a power of, I already did it, 1.7 watts. Which is a little bit, that seems reasonable. That says if I have a phone size like this, and I put it in the sun, I mean 1.7 watts, which is what I get out of it. It's kind of hard to judge wattage, but that seems, I'm okay with that. It's not crazy, okay? This is just an estimation. So that's my power. Now let's do the following. So here's my battery, my energy. There's my power. Let's find out how long it would take to charge that amount. So I can say power from the sun is the change in energy over the change in time. The change in time is going to be equal to the change in energy over the power. And so now I have 3.6 times 10 to the 4th joules divided by the power of 1.7 watts. And I get a time of, did it already, wrote it down. Where did I write it down? Oh, let's see. I get, hold on one second. I didn't write down this part. I converted it. Just so you can check your numbers. 2.08 times 10 to the 4th. Seconds. And then if I divide that by 3600 to get it into hours, I get delta T is 5.7 hours. So if I put my phone in the sun, it has to be in the sun at least an average of 45-degree angle for almost 6 hours to charge. So could you do it? Yes. Should you do it? It's probably not worth it, because that assumes also you're not using the phone, right? Because if I'm using the phone, then that's going to have to keep up with my usage too. It wouldn't hurt, but it wouldn't really help. And on top of that, where's your phone most of the time? It's usually in your pocket. So it adds to the extra cost of the phone, it adds to the extra bulk of the phone, and it just may not make sense. If you had a bigger solar panel, that would help out a lot. Even, good size, like 0.1 square meter or something like that, that's actually pretty big. You could get significant power out of that. But that's why you don't see solar panels on your phone all the time.